Hello everyone and welcome. This is the video for lesson 1-3, Parent Functions and Transformations out of the Big Ideas Algebra 2 textbook. Let's take a second and look at our learning targets for the lesson. So what you want to do is you want to be able to identify the function family to which a function belongs. The second one is to graph transformations of functions. That one we're not going to focus on quite yet because we do have the ability to use Desmos, but we're going to focus much more on the third one. I can explain how translations, reflections, stretches, and shrinks affect graphs of functions. So let's get to it. So we're going to begin with identifying function families, and if you got your highlighter handy, we're going to highlight all 4 of the families that we're going to talk about in this lesson, and we're going to start with constant. And if you notice, a constant is a flat line. It is perfectly horizontal, and the function is going to be either f of x or y, and it's going to be equal to a number. It's not going to be equal to x. That's why it's flat. So that one's pretty easy to identify. If you ever see a horizontal flat line, it is going to automatically be a constant. So the next family is the linear function family. That is also a straight line, but it's going to have some kind of diagonal. It could be vertical. It's going to have a slope to it, whether it be undefined. Now, a constant has a 0 slope, but linear specifically, it's going to have some kind of diagonal to it, unless it is straight up or down. So that's the only difference between those two. And we'll talk about the domain and range of all of them in a minute. Let's go ahead and scoot to absolute value. So next up is absolute value. You can tell that that absolute value is a V. It could be a happy V or it could be an upside down V. It depends on if it's reflected or not, but it's a V. And then quadratic is the U shape. We call those a parabolic shape or a parabola. It could be a happy U, like a smiley face, or it can be a sad U, like a frowny face. So that's how you identify it using the shape. So let's talk more specifically about the function. So I think I mentioned before the constant is going to be equal to a number. And then linear, on the other hand, is going to be equal to x. And it could be equal to 2x. It could be plus 3, whatever. But it's going to have x, and it's more specifically x to the power of 1. If you look at your absolute value, that one is going to have those bars around the x. So the absolute value bars, it's going to look like a V when you graph it. And then quadratic, of course, is squared. While it's not a big focus in today's lesson, I do want to talk about the domain and the range just for a little bit for each function family. The domain on a constant is going to be all real numbers. And actually, if you look all the way across, the domain is going to be all real numbers for all of these. And the reason why the domain has all real numbers is that each one of these arrows is going to point to the left and to the right. It may be pointing up or down, but domain is where the graph exists from the left to the right. And, you know, while this one might be kind of an extreme up, but it's also pointing to the left. So anything that's going to be pointing to the left and to the right has no restrictions on the domain. We're automatically going to say that it's all real numbers. Range, on the other hand, you're going to be looking where the graph exists vertically. So this constant right here is very limited. It's limited to that one place where it hits it on the y-axis. It does not go up, it does not go down because it's flat. So whatever number it's equal to is going to be the actual range. That's it. That's all you're going to have. Linear, on the other hand, see how it goes up and down? There's no limitations. So it's also going to be all real numbers. Now, absolute value, on the other hand, look at the arrows. Both of them are facing up. So they don't. If it doesn't go down continuously, it's going to have a limitation. So what you're going to have to do is you're going to have to look at the very bottom, or if it's reflected, the top of the V. And sometimes it's going to be greater than 0. Now this is the parent function, so it's going to be greater than 0 on the y-axis. If it's been flipped over, it'll be less than that. Same thing with quadratic. They are both pointing up. Nothing is going to continually go down, so the range is limited. So you're going to have to either look at that maximum or minimum. In this case, your minimum here is 0 on the y-axis, and your range is going to be everything 0 and above on the y-axis. Okay, let's scoot on to a little bit of practice, we want to identify the function family. We are either going to choose whether it is a constant, a linear, absolute value, or a quadratic. And I probably, well, no, actually, I was going to say I probably should have put some equations in here, but they are in here. So awesome. We have the shape and we have the equation. So let's look at our first example here. I can immediately recognize the shape. It's that U shape. It is a parabola. If you look at the key right here, see how it's squared? It's going to be an x squared. That is quadratic. Okay, I'm going to do the next one. That one is obviously, due to its shape, that is a V. So it is an absolute value graph. And if you notice in the equation, it has the little bars right here indicating that is an absolute value equation. Spell it right. Here we go. All right, at this point, if you want to just go ahead and pause the video, take a guess on the next three, and then just replay, and let's see how you do, okay? All right, last three. This one right here is a straight line, but it's not flat. So since it's not flat, it is going to be linear. And if you look at the equation, you know that it's linear because it's just got x, and it is x to the power of 1. This one right here, oh, there we have it. We have our flat line, and it is equal to a number, so it is definitely going to be a constant function. And the last one is at U shape. It has been reflected, so it doesn't look just like the parent graph, but it is a parabola, and we say quadratic family. It does not have the equation on there, but I know if I wrote the equation for it, it would be x squared on some level. So this next part right here, describing transformations, this is very foundational. That means that you will absolutely need to know that, and it's the same for the beginning of the lesson too, but this will be revisited in chapters 1, 2, 3, 4, and I think a couple more after that, but it's very, very important that you master the different types of transformations. So the first kind of transformation is just any kind, it's like a generic change. It's the shape, the size, the position, the orientation. So it could be flipped over, it could be shifted up or down, it could be lots of different things. Okay, so this is kind of more of a generic thing. More specifically, though, is called a translation. So when you translate a graph, you're going to translate it up or you're going to translate it down. So you can move it up, down, you can move it left or right. So it can move either horizontally or it can move vertically. Translation, almost like slation, slide. You're sliding it up, down, left, or right. You're not really changing the shape of it. Now, reflection, that one's pretty obvious because if you look in the mirror, if you look in the water, it will reflect your image. And it's exactly the same thing on a graph, except for when you reflect on a graph, you're going to reflect typically over the x-axis or the y-axis. And we're going to talk about what that looks like and how it affects the functions in just a minute. And the last thing we want to talk about is a stretch or a shrink. Now that's going to actually change the shape of the graph. It's going to like either pull it or it's going to compress it, almost like a rubber band. And in this class in Algebra 2, we do heavily focus on the vertical stretch and the vertical shrink, not so much horizontal stretch or horizontal shrink. So let me bring up some Desmos and I will show you some examples of all of those. Okay, so I've got our Tennessee Desmos app. Just make sure when you're using Desmos that you are using the Tennessee version. You just do a Google search of Desmos Tennessee and it'll pop up for you. The two graphs that we're going to focus on the most is going to be an absolute value graph and a quadratic graph. So currently I've got a quadratic graph and I have the parent graph in the first line and I have the one that I'm going to modify or transform in the second line. So right now you can see that they're like kind of one right on top of each other. So if I wanted to move this thing up, so moving it up, I'm going to add to the function itself. So when you translate things, it's either going to affect the entire function or it's going to affect just the x variable. So I'm going to add anything I want to here. Let's say I want to add 5. So all of a sudden that blue graph shifted from 0 up to 5. So all of these individual little points in this red graph have now shifted up 5. It looks like the shape of the graph has changed. It has not. It has just gone up. Now, if you subtract 5, that's going to have the same effect, except for it's going to move all of your y values down. So subtracting from your function is going to make it go down. Now, how do you make this thing go left and right? It's not what you think is going to happen. So first of all, left and right, it's going to affect the x variable. You would think that moving this 1 to the right, you would add 1 to it, but it's actually the exact opposite. So a good rule is whenever you're messing with the x variable, if you're trying to translate it, stretch it, shrink, all the stuff, reflect it, it's gonna be the opposite you think, okay? So if I add 1, it's actually gonna go left 1. So plus 1, see how the blue moved to the left 1 spot? And if I change that to minus 1, it's going to move it to the right. So left and right will have the opposite effect that you expect it to. I'll show you one more time. Let's change it to 3. So if I subtracted 3, it's going to move all of the x values to the right 3. Yep, there it goes. And if I add 3, it's going to move everything to the left. And that's the same. That's true for any other function that we study. So I just showed you the 4 different types of translations because I could slide it left, right, up, and down. I'm going to show you what it looks like to reflect. So a reflection is when you multiply either the function or the x variable by -1. So if I put a -1 out in the front, now it might not have the 1 there, it might just have a negative, look what happens. So that blue reflected over the x-axis. All of these y variables are now negative. 0 stays the same. It's really hard to tell on this one, but like 1, 1 right here. Here it is, 1, 1. So 1, 1 actually reflected all the way down here to be 1, -1. When you multiply the function by -1, what it does is it changes all of your y values. So in front means it's going to reflect over the x-axis. Now this is kind of neat. If you put it in front of the x, it doesn't reflect it over the x-axis. Remember, it's like opposite world. It actually reflects it over the y-axis. And if you look, the y-axis is a line of symmetry of a quadratic function. So if I put negative here, you're not going to see anything. So what's happening is that this point that's here has reflected over to the left. All of the things on the left is now on the right, but it's still in the exact same position. So if you try to reflect an absolute value, if you reflect a quadratic function over the y-axis, you cannot see it in the graph. You can only see it in the function itself. So that's very important. Okay, and last but not least, we're going to talk about the vertical stretches and vertical shrinks. Now, we're not talking about horizontal stretches and shrinks, so I'm going to stay away from the x variable. I'm going to have to put everything in the front. So if you want to stretch, you're going to have to multiply the entire function by something greater than 1. So if I stretch everything by a factor of 2, I'm going to multiply the function by 2. So that red looks like it's actually been pulled up. So all of these points right here, so let's start with 1, 1. This point, let me just graph 1, 1. Okay, there it is. That's 1, 2. Let's try it again. 1, 1. So 1, 1, when you stretch a graph by 2, you are multiplying the function by 2. You're literally multiplying the y coordinate by 2. So do you see what happened? This green dot right here was actually pulled up twice its value. So this will double in size to here. Now, if you have another one, I know that I have 2, 4 on my original graph. 2, 4 is still going to be at 2, but the y value will be doubled. So the 4 will now become 8. So the green dot has been pulled twice its distance away from the x-axis. So when you stretch something, you're pulling it away from that x-axis because it's stretched vertically. Now, if you want to go the opposite direction, instead of stretching it, what you're going to need to do is you're going to want to shrink it, and your book calls it a compression. So instead of multiplying it by something greater than 1, you're going to multiply it by something between 0 and 1. If you go negative, that means it's a reflection. It's no longer going to be a stretch or a shrink. So negative is a reflection. You have to multiply it by something between 0 and 1. So if I multiply this by 0.5, what it'll do is it will make it look like it has been squished. So this original point at 1, 1, right here, is now going to be half the distance it was to the x-axis. So it'll still be at 1, but the new point will be half the distance away. Another point on here is 2, 4. So if you start with 2, 4, what is going to be half that distance? So it's 4 away, half the distance would be 2. And that's how stretches and shrinks work. All right, so I showed you quadratic functions and all the different types of transformations. So let's go into absolute value. Same situation. I've got my parent graph right here in line 1, and then I'm going to manipulate line 2. So I'm going to put plus 3 here. What do you think is going to happen? I'm going to do plus 3. It went up. Okay. What's going to happen if I change that to minus 3? Down 3 places. Okay, so instead of me adding and subtracting from the function, I'm now going to add and subtract from x. So what's going to happen if I add 2 to the x? It went left. So anything that affects the x is going to have that opposite effect. And once again, if I subtract 2, it's going to make it go to the right 2. Okay, let's talk about reflections. So if I want it to reflect over the x-axis, I'm going to multiply the function by negative 1. You see how it flipped over the x-axis there? If I want it to reflect over the y-axis, now remember, it's symmetrical up and down this line right here. See? You don't see anything. So that is reflecting, but you don't see the effect because it's symmetrical already over that line. All right, if I wanted to stretch this, if I wanted to pull the y values up or away from the x-axis, if I wanted to double that value, I would say times 2. If I wanted to triple those values, make it skinnier, pull it 3 times, okay? If I wanted to shrink it or compress it, I could do 0.2. It's going to make it very flat. So it's multiplying all of those y coordinates by 0.2. If I wanted to half the distance, so you can kind of see it right here. So this hits at 5, 5. So half the distance, if you instead of going up 5, half the distance would be going up 2.5. So that is a visual representation of what happens and what you've got to do to your functions to make those transformations happen. So if you're feeling a little bit overwhelmed with all that information, it's completely understandable. It is a lot of information, but like I said, we are going to redo it in chapter 2 and chapter 3 and chapter 4. And last year, my students did so much better, but it's very important that you actually practice. Don't just guess, like really, really, really try, because this is not going to go away. You do need to be really good at it. So let's practice. Let's go ahead and finish our notes. It says to describe the transformation from f of x to g of x. So which one is our parent graph? Our parent graph is this one right here. So it's originally this black parabolic function right here, and it looks like it has flipped or reflected over the x-axis, and you can kind of see that right here. So that's all we got to do. We just have to state what happened. So it has reflected over the x-axis. And if you say that it reflects, you have to say if it reflects over the x or the y-axis. Okay, these are absolute value graphs. This is our parent function because it's just the absolute value of x. And it looks like we have added 1 to the x. So our parent function is here. And look what happened to our graph. It moved to the left. So that makes sense. So if I add 1 to x, it's going to actually translate it. So we're going to translate it because remember that's a sliding pattern. So translate left. How many did it translate? It translated left 1 place. Okay, let's look at the next one. We have a parabola again. This is our parent graph here. And if you notice, this looks like everything has shifted to the right 2 places. And that makes sense because if you're taking away 2 from the x, it's going to make it move to the right. So I'm going to translate 2 to the right. And our last one is also a parabola. This one's a little bit trickier. So you can see that our original one is right here, and it looks like the graph has been pulled up, so that's going to indicate a stretch. And you can kind of see that if this is at, I think this is 2, the 2 is now going to be a 6. Let me look. Okay, so I have to pay attention to the scale here. So this point is at 2, 4. If that's at 2, 4 and the point has been stretched all the way up to here, see how this is 8? This is actually being stretched all the way up to 12. So that point is now 2, 12. Now look what happened. It went from 4 to 12. It's multiplying it by 3. So 3 times 4 gives you 12. So this is going to be a vertical stretch by a factor of 3. It's a lot easier to look at the equation than to look at the points, but you can look at the points. So I put a little table in here that might help you kind of identify what's going on with the functions. Just remember that f of x just represents the equation that you're trying to manipulate. So if you're adding, it's going to make it go up. If you're subtracting, it's going to go down. Same thing with the x's. If you add to the x, it's going to go left. If you take away from x, it goes right. If you multiply the function by -1, so if the negative's in the front, it's going to reflect over the x, and if the negative is in there with x, it's going to reflect over the y-axis. And then a vertical stretch, you have to multiply the function by something greater than 1, and if it is a compression or a shrink, it's got to be between 0 and 1. So that's kind of a little cheat sheet right there. That is not in your textbook. Okay, so this time we have no graphs. We have to look purely at the equation and figure out what's going on. So what I want you to do first, I want you to figure out, well, what's the parent function? So you see how this is like a little square here? That gives me an idea that I do believe that is going to be a parent function of x squared. So it's a parabola. I know what it's going to look like. It's going to be a U shape. Here's what you need to do, though. You're going to play detective. You're going to figure out what has changed. It looks like the x has a +2 added to it. See how it's in the parentheses with the x? And then I also have a -5. So remember, when you have something being added to the x, let's look over here. So if you're adding to the x, what happens? It goes left. So I'm translating this to the left 2 places. So translate left 2. What does that -5 do? So the -5 is at the end. You are subtracting from the function. That is going to also translate it, but it's going to go down 5. Okay, so moving on to the next one. What is our parent function going to be? It looks like I've got these absolute value bars in here. So that is our parent function. And now what we have to do is we have to figure out all of the ways that this parent function has changed. So it has a negative in front of it. It has a +5 with the x, and it has a -3 at the end of the function. So what I'm going to do is I'm going to write these down individually. If I'm multiplying that function, do you see where it is? It's in front. So that means it's a reflection, but it's a reflection where? It's a reflection over the x-axis. And if you are adding 5 to x, adding 5 to x means that it's going to go the opposite direction. It's going to go left 5 and -3. And that's at the end of the function. You're going to bring everything down 3. All right, this is the last one of the table. So I'm going to try to figure out the original parent function, and I see absolute value bars in here. So it started out as the absolute value of x. Looks like there's only one change though. It's been multiplied by 3. So that 3 is on the outside. If I'm multiplying by 3, what that does is it either stretches it or shrinks it. So I know it's going to be a vertical change, but that 3 is greater than 1. So if you multiply by something greater than 1, it's going to stretch it by a factor of 3. So this last one's kind of a real world type situation where you've got a table, we've got the height of a dirt bike after so many seconds after jumping off a ramp. Now I think you could probably imagine a dirt bike jumping off of a ramp in that kind of pattern or path it's going to follow. But we do have some points that we can graph, and I put a little graph over here for you. So let's go ahead and just make a little scatter plot, 0 and 8. So 0 and 8, and each one of these lines vertically is 2, 0.5 and 20. So 0.5 is going to be halfway here. It's going to jump all the way up to 20, and then 1 I do believe is 24. And then 1.5, so 1.5 falls back down to 20, and then after 2 seconds, he's hanging out about 8, is it 8 feet? Yes, 8 feet in the air. So that bike is kind of follow this pattern right here. So I know that this is going to be a quadratic. We don't know how to do this yet, but if I wrote an equation, it would be like y equals x squared, and it would have some modifications to it. Then it says to estimate the height after 1.75 seconds. Well, if that's 1.5, it's going to be halfway between that and 2. So it's going to be about right here. So let's kind of scoot up. It's about here-ish. Over here, so 10, 12, 14. I don't know. Good guess is about 15. It's asking you to estimate. So my estimate is 15 feet in the air. All right, just let me know if you've got any questions on anything, and have a great day.